Okay, so it's the last lesson in Chapter 4. These two outcomes are not in the textbook, so make sure you get these notes, you pay close attention to what we're about to do. It's actually not tough. You just have to work with these two new formulas that we're going to develop here. The first one is called the distance formula. The distance formula tells you how long a line segment is. Recall that a line segment is a piece of a line, and it has end points. By definition, a line goes forever in both directions. That's why we usually put arrows on them when we graph them last unit. But this is going to be an actual line segment. Here, I'll even draw it. It goes from A to B. A is where it starts, B is where it ends. Make me a nice straight line. And what I'd like to know is I'd like to know how long that line segment is. How far is it to get from A to B? You might be saying, well, I can go up to and over 1, 2, 3, 4. Well, that's not a straight line, though. How far is the distance straight? There's people who might go, well, you go 1, 2, 3, 4. Well, wait a minute. That's not exactly straight lines. It's not going to be 4. Any ideas? How would I find this distance? Well, okay, maybe you can think back to grade 8. You could use Pythagoras to find this distance. You realize that if you go straight up 2 and 4, then you can figure out we can use Pythagoras, and we can say that, all right, because of Pythagoras, I'll call this distance d for distance. Well, let's see, it's 2 squared plus 4 squared equals d squared. Now, normally, back in grade 8, you learned to let's square those numbers and figure them out first. But suppose I wanted to do it in a different order. Suppose I wanted to make it look like that. Why? Because I like the way that looks. That looks very nice to me. Distance is the square root of whatever the heck 2 squared plus 4 squared is. All right? So distance is the square root of 4 plus 16, right? So my distance is the square root of 20. Aha! There we go. So we know, because we just finished a unit on radicals, that this is not even a rational number. There's no decimal I could give you that terminates or repeats. I can't make that a fraction. So either I give you an estimated, like it's approximately 4.5, or I could say that it is exactly the square root of 20. Remember, I can simplify that. I could also say that it is exactly 2 root 5. But one way or the other, all three of these things represent that distance. Kind of mind-blowing that something as simple as a line that connects 2 points could be a number that I can't even write to you with a fraction. But that's exactly the way math works. Okay? Now, let's think about this in a different way. A is a point. It has coordinates. Those coordinates are 2, 1. B is a point with coordinates. Its coordinates are 6, 3. How did I figure out that this line was 2? Well, I counted the things. But what if I wasn't looking at a picture? What if I just told you the coordinates? Well, I could figure out that this distance was 2 because this distance here, this 2, is really the result of going x2 minus x1, if this is my x2 and this is my x1. Okay, oops, sorry, my bad. Those are the y's. Whoops. Right, this height here is the second y coordinate minus the first y coordinate, 3 minus 1. That's where this 2 comes from. This point's 3, this point's 1, 3 minus 1 is 2. And this 4 distance here, I can get by going, well, it's the second x-coordinate minus the first x-coordinate. So I could have gotten this 2 and this 4 by saying it was really, well, again, I got the 2 by going 3 minus 1 squared. And I got this 4 by going 6 minus 2 squared. Now, what if I wasn't using specifically these 2 points? Well, Again, this was the second y coordinate, the first y coordinate. The second x coordinate, the first x coordinate. I feel a formula coming on. The formula for the distance between any 2 points, because it really just comes from Pythagoras, is that distance equals the square root, I'll put the x's first, of x2 minus x1 squared plus y2 minus y1 squared. And that is my formula. Put a nice big cloud around it. It's on your formula sheet. You don't have to memorize it, but you do have to know how to work with it. Now there's people going, well, wait a minute, you switched the order. You did the y's first up here. Does that matter? I can add 2 numbers in any order I want. Here's something interesting. I decided, it was kind of arbitrary for me to call this the second y coordinate. What if I had called this x1 and y1? Would I have gotten a different answer if I'd have had this? Let's think about that for a sec. Will these two things make different numbers? This is 2 squared. This is negative 2 squared. This is 4 squared. This is negative 4 squared. Will those answers be different? And there's already people shaking their heads. No, obviously they won't, because squaring 2 and squaring negative 2 is the same number. So it doesn't even matter which point I call x1 and which point I call x2. It doesn't matter if I say that's the first point and that's the second point, or vice versa. The formula works either way. Okay? Let's prove it. Let's do some examples. First one is down here. All right, I need coordinates on this thing. I know you're saying, well, why don't we just count and use Pythagoras again? Nah, I want to use my fancy new formula. I just brought it home and got it out of the box. I want to see how it works. So let's see. That v coordinate is negative 4, 3, and the w coordinate is 4, 0. Now again, it doesn't matter which one I call first and second, but I'm a left to right reader, so I'll call that x1 and y1. I'll call those the first coordinates. And I'll call this x2 and y2. Okay, so let's write the formula down again. The distance between any 2 points is x2 minus x1 squared plus y2 minus y1 squared. Let's put in those numbers. So my distance is 4 is x2 minus, careful, minus negative 4. You could add another bracket there if you want to. Don't lose that negative. Plus, okay, now my y coordinates. y2 is 0, and y1 is 3. There we go. So my distance formula spits out 4 minus negative 4. What happens when you minus a negative? You add a positive. So 4 plus 4, essentially, that's 8 squared plus negative 3 squared. That's going to equal 64 plus 9. So that answer is the root of 73. And then, depending on my situation, say that this distance represented an actual measurement in the real world. Then I'd take my calculator, I'd square root 73, and I'd put an estimated decimal for the answer. If I just wanted the most exact answer, I'd leave it like this. This is not a simplifiable radical because I don't think there's any perfect squares in 73 other than 1. Nope, there isn't. Just thought about it. So there you go. That's my answer. Now you can see why we didn't put this stuff with the graphing unit, because look at how often. We've only done 2 examples and already both of them had radicals in them. Okay? So there we go. So that's the distance formula. Now, like I said, did I need this picture? Not really. The formula works independent of the geometry. So for the next example, ignore the picture completely. In fact, the fourth example, they don't even give you a picture. Let's just run the formula. Distance is the square root of, okay, let's see, x2, so I'll call that 1, minus negative 1 squared, and then y2, which is 4, minus negative 2 squared. Everybody see that? Okay, so that's going to be distance is equal to the square root of, that will be, I'm missing a bracket there, aren't I? There we go, that's better. That's going to be 1 minus negative 1 is 2, 2 squared. And 4 minus negative 2, and again I'm missing a bracket, sorry, sloppy here. 4 minus negative 2 is 6, so that's 6 squared. So my distance between these 2 points is going to be whatever the square root of 4 plus 36 is. I'll write that out. which is the square root of 40. Okay, I could, again, if I have a calculator, I could get you a decimal on that. Does that one simplify? Any perfect squares in 40? Yeah, 4. Okay, so it's actually 2 root 10. All right, and like I promised, I don't really need that picture. Let's just formula this thing out. We'll call that x1 and y1. We'll call that x2 and y2. So my distance is, here, I haven't seen the formula well. I'll write the formula out again. x2 minus x1 squared, add y2 minus y1 squared. Okay, so let's plug in the numbers. It's 3 minus negative 2 squared plus negative 6 minus 4 squared. And then this just comes down to make sure you're good with your integer skills. Careful, that's 5 squared. And that's negative 10 squared. Okay, squaring 5 gives you 25. Squaring 10 gives you 100. Remember, the negative goes away when you square it. So I'm getting the square root of 125. That's a pretty good raw answer. And again, either I take out my calculator and give you a decimal, or I realize that that simplifies down to 5 root 5. I don't really care. If it says simplify your answer, they want that. Okay, what can you use the distance formula for? Let's use it for a problem. This is a good problem. I like this one. Determine whether the following triangle is isosceles. Who remembers what isosceles means? I see some people putting up their hand with 2 fingers. That means that's right. They've got the right idea. 2 sides are the same, the other one's different. They can't all be the same. That'd be equilateral. So, prove that it's isosceles. Okay, so I would like to know the distances for all these lines. First thing I'm going to do is I'm going to put coordinates on them. W is negative 3, 4. U is 1, 6. And V is 2, negative 1. Now, if this is isosceles, 2 lines are the same distance and the third one's different. So I'm going to find 3 distances. I'll do the distance from V to W first. So that's going to be negative, I'll do the x's first. 2 minus negative 3 squared plus, so 2 minus negative 3, negative 1 minus 4. And the distance from W to V is, again, I keep missing a bracket. That's 5 squared plus negative 5 squared, which is 25 plus 25, so the square root of 50. So that's the distance from here. I'll put it on my diagram. Root 50. Let's do U to V. The distance from U to V. Dov. All right. I'll take this one first. 1 minus 2 squared, and then 6 minus negative 1 squared. So that's the square root of 1 squared plus 7 squared. Hey, that's not looking quite like that. Ah, but look at the math. Haha! Those 2 lines are the same. But wait a minute, I haven't actually proven it's isosceles yet. If it's isosceles, this line can't be the root of 50. If it is, it's not isosceles, it's equilateral. Remember that? So, one last distance formula. The distance from W to U. That would be 1 minus negative 3 and 6 minus 4. So you better not be the root of 50 or something's wrong with my logic. That's going to be 4 squared plus 2 squared. Oh yeah, that's nowhere near the root of 50. That's going to be the square root of 16 plus 4. It's the root of 20. Therefore, triangle W, oh, I'm off the screen, sorry. Triangle W, U, V is isosceles. And if I had to say why, because 2 sides are equal and the third side isn't. So there we go. That's the distance formula. I got an even easier formula for you on the next page. Give you a sec to catch up to me here. Okay, flip the page. The midpoint. So we just learned how to find the distance from one point to another. The midpoint from one point to another, I'll say the midpoint between two ends of a line segment is the average of the distances between their coordinates. That's more complicated sounding than it is to do. How do you find the average between two numbers again? How do you find the average between two numbers?
You just half them.
You half them?
No, you divide, you add them and then divide it by 2.
Beautiful. You take the x coordinates, you add them, divide by 2. You take the y coordinates, you add them, divided by 2. Beautiful. And that's it. That's the formula. Happy cloud. That's what it'll say on your formula sheet. Notice that the last formula gave me a number, right? The distance between 2 points was a number, a distance. This is giving me two different coordinates, an x coordinate and a y coordinate. Somewhere there is a place between P and Q where I am halfway between them. And that place is the average of the x coordinates, the average of the y coordinates. They're calling it M here. Somewhere in here, in this example, let's do the example, somewhere there's an M. Somewhere there's a point halfway between C and D. What is it? It is x1 plus x2 over 2, y1 plus y2 over 2. So let's see. We need the coordinates then. So C has coordinates 2, 1, and D has coordinates 4, 7. Once again, does it matter which one I call x1 and x2? No, because I'm adding them. You can add two things in any order you want. You get the same answer. So I have 2 plus 4 and 1 plus 7. Finish that up. You get 6 over 2, which is 3, 8 over 2, which is 4, and there it is. Let's see if that looks right. The midpoint should be 3, 4. 3 over, 4 up. Yeah, that looks pretty good. That is the midpoint of that line. Here, I'll give you a sec to catch up to me. These are such nice little formulas. Now the distance formula gave me radicals sometimes. This one won't ever give me radicals. Sometimes, though, it'll give you fractions. I think example 2 is going to end up being a fraction. Just like the distance formula, do I even need the picture anymore? No, I just need the coordinates. So my midpoint here is going to be the average of my x coordinates, -3 plus -8 over 2. And 5 plus 1 over 2. So the midpoint between A and B, I don't even need a graph to look at it, will be whatever -11 over 2, comma, 6 over 2 is. And there you go. 6 over 2, no problem. That makes a 3. But what can I do with 11 over 2? Well, I'm just going to leave it as 11 over 2. I like improper fractions that are simplified as the best answer. If you prefer, you could make it a mixed number. That would be -5.5, comma 3. Or I guess you could even make it a decimal. -5.53. All the same. And that's the midpoint formula. So that's it for this chapter. Those are the last two things. Basically a throwback to graphing.